There are many basic results in all branches of mathematics, really, certainly abstract algebra analysis, that depend on this thing called the Zorn's lemma. Some results in abstract algebra would be things like any vector space has a basis, or say any commutative ring with 1 has a maximal ideal, or say any field has an algebraic closure, meaning it can be put inside a bigger field where every polynomial with coefficients in this bigger field has a solution in this bigger field, etc. And it's called a lemma, but it's really logically equivalent to axiom of set theory. So one of the statements in foundational axioms of mathematics called axiom of choice, which usually when you are doing mathematics, you assume most working mathematicians do. So I want to talk about this Zorn's lemma a little bit. And I have the statement on the left here, but as you can see, there are many words that need to be explained. So on the right, I have tried to explain them. So you have to talk about order relations. So let's take from the top on right, a partial order denoted by a less than or equal to sign on a set P is a relation on P satisfying three properties called reflexivity, antisymmetry, and transitivity. So first one says A is less than or equal to A for every A in P. The second one says that if two things are less than or equal to each other, then they better be equal. And the third says that if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. So I have sort of a picture of a finite partial ordered set on the top right there. You can, where P is the set of those little circles, and the lines tell you who is less than or equal to who. For example, if you take this guy and his grandchild, I'll say A is greater than or equal to B. But if you take B and a cousin of B, then between B and C, I'm not saying who is bigger than who. So I'm not saying that two things can always be compared. So that's the word partial in partial order. That's why we call it a partial order. A poset is just an abbreviation for partially ordered set. So a poset is a set together with a partial order on it. A partial order is called a total order if any two elements can be compared, meaning for any A and B in P, either A is less than or equal to B or B is less than or equal to A. So this is the kind of ordering you have seen on real numbers or rational numbers. If you give me any two real numbers, one is always less than or equal to the other. So on that poset that I have drawn up on right, that's not a totally ordered set because there are incomparable elements. If P, less than or equal to is a poset, a totally ordered subset of P is called a chain in P. Okay. So the picture I have on top, that's not totally ordered, but if I only take the green subset, these four dots, that's a totally ordered subset. So that will be a chain in P. Here is another chain. Okay. But if I add, what I have marked out in green now, those 5 dots, that's not a chain. Because this spot was not comparable, that 5th dot. Okay, so that's what a chain means. The name is kind of self-explanatory. Then I need to have a notion of an upper bound, which means the usual thing. An element of a so if you have a subset S of a partially ordered set P, an element of P is called an upper bound of S if A is greater than or equal to every element of S. look, I'm not insisting that A belong to S. I'm only insisting that A belong to P. So for example, if you take this yellow set, these three dots, A will be upper bound for this set. D would be another upper bound. Okay? So it doesn't have to belong to. The green set, if you look at that chain, A is still an upper bound for that, but D is not an upper bound for that, etc. And then finally, the notion of a maximal element, it just simply means an element such that there is nothing strictly above it. So you say A in P is a maximal element if whenever B is in P and B is at least as big as A, then B better be equal to A. So again, in my picture, here is a maximal element because there is nothing above it. It's certainly not the biggest of all. There are other things that are not comparable to it. It just means that there is nothing above it. A is another maximal element. D is another maximal element. This is another maximal element. And I think those are all in this picture. Okay. So now that we have explained all this language, I can state the Zorn's lemma. If P is any poset in which every chain has an upper bound in P, then P contains a maximal element. So you have a poset, and if you give me any totally ordered subset here, totally ordered subset, any chain, then I can find something in P which sits above it. That's the assumption. And then the conclusion is that P has some element so that P contains some element such that there is nothing strictly above it. There's nothing strictly above it. And I don't know what your intuition about this statement is. I don't have a very strong intuition. But it turns out that it's logically equivalent to another statement which is usually taken as an axiom in set theory, so an axiom of foundation of mathematics, if you will, called the axiom of choice. And I've written that out here. And this one sounds a lot more intuitive to me, at least. Let's move this up. This one states, if you give me any set of sets, there is a choice function on it. Meaning, if you have any set of non-empty sets, I should say non-empty, then there exists a function from that set to union of all the elements of this set for such that f of a set belongs to that set for every set in I. This might sound confusing, but a picture will say it much better, I think. So here's a picture for it. Here's a picture of I. I is a set of sets. So here is a set in A, so a set in I. Here is another set in I. Here is another set in I, etc. Given, so you can think of I as a box which contains many boxes. A box called A box called A prime, a box called A double prime, etc. Now what it's saying is that I can construct a function from I, meaning from this list, to the union of all these sets, meaning all these dots, so that f of A is in this box. So I can choose, that's why this is called a choice function. I can choose an element of A. I can choose an element of A prime. I can choose an element of A double prime, etc. So there exists such a function. Sometimes it's stated as follows, maybe which will sound even more intuitive. It says, if you assume that these sets A prime, A double prime are all disjoint, then what it says is that you can make a new set, which is really in our language the image of this function f. You can make a new set which consists of exactly one thing from all these sets. Namely, you can just put these guys, etc. So I'll repeat. Given a set of non-empty disjoint sets, there exists a set C which contains exactly one element from each of those sets. That's what it says. So you can choose, if you imagine these as boxes of things, you can choose one thing from the first box and put it in here, choose one thing from the second box and put it in here, choose one thing from the third box, put it in here, etc. And if you state it like that, and you can make this new box of things called a choice set. Now if you state it like this, it sounds much more intuitive to me, that it's true. But the catch, of course, is that this set I might be huge. If it's a finite set of things, then sure, this I can understand, countable even. But beyond that, who knows what's going on? So in those circumstances, this becomes a rather hairy statement, which has some rather non-intuitive sounding consequences or equivalent statements. So here's a third statement, for example, which is also equivalent to this, called well-ordering principle. So now I have three versions of the statement. One is called axiom of choice, one is called Zorn's lemma, one is called well-ordering principle. And this one says that every set can be well-ordered. And this one sounds very non-intuitive to me, rather counterintuitive. So what does that mean? First of all, a well-ordering, I have it on the right bottom here, a well-ordering on a set is better than total ordering. So a total order on a set P is called a well-ordering if given any non-empty subset of P, there exists an element in that subset, I emphasize, in that subset which is less than or equal to every element of that subset, meaning that's a least element of A, the smallest element of A. Smallest element of A. So any non-empty subset contains the smallest element. And this is very strong. I mean, like if you take the usual ordering on rational numbers, you can look at the subset of all fractions that are strictly between 0 and 1, so the open interval in rational numbers, so to say. That has no smallest rational number. And there is a number which is smaller than all of them, 0 or even any negative number, but those are not in the subset. So that shows that the usual ordering on rational numbers is not a well-ordering. Ditto for real numbers. The well-ordering that you are familiar with is the usual ordering on counting numbers, natural numbers. So there we do know that if you give me any non-empty subset of natural numbers, then it has a smallest element. All multiples of 3 has a smallest element 3. And this statement is actually equivalent to the principle of induction, so we use it all the time, this well-ordering axiom of natural numbers. In fact, you could use a bijection between natural numbers and rational numbers to find a well-ordering on rationals. And that would look very different from the usual ordering on rationals. But just try to picture a well-ordering on real numbers. And if you think about this a while, I think you'll realize why this well-ordering principle is so non-intuitive. You just cannot picture a well-ordering on real numbers, how it looks like. So it's very the existence of this well-ordering on real numbers will be a consequence of this axiom of choice. And this is very non-constructive. You see, it says that you can construct this function, but it doesn't provide you with such a function. So there we are then. So we have these three statements. All of them are logically equivalent, so you can work with any of them, and it has lots of important consequences. One sounds very intuitive, one is sort of in the middle, and one is very non-intuitive. Just shows that you should be careful when you use them.